Sign convention for work. Consider the system. Work done on the system. Another work transfer is work done by the system. Work done by the system. Work done on the system, the sign convention is negative. Work done by the system, the sign convention is positive. For example, we can consider air compressor, where work has to be done on the compressor to convert the low pressure air to high pressure air. Now, work done by the system, very good example is turbine, the power generating machines that is you can consider it as a water turbine, where high pressure water will go as a low pressure water in the expense of work done by the system. Therefore, work done on the system, negative. Work done by the system is positive. Same thing, I'll continue here by considering the two processes, expansion process and compression process. Work done by the system in the expansion process in a PV diagram. If I write like this, one process changing of state from 1 to 2. This is the expansion process where volume is increasing, and pressure is decreasing. This is expansion. Same thing if I write a PV diagram for a compression process, any process, the changing of state from 1 to 2. In a compression process, volume decreases, and pressure increases. This is expansion. Area below this particular curve, the corresponding volume is V2 here, and the corresponding volume here is V1. Area below the curve in a PV diagram, any curve in a PV diagram, it is work done. This is also work done during a compression process. This corresponding volume is V2 and this corresponding volume is V1. Area below the curve in our PV diagram, that is work done. This is the work done during a compression process, work done expansion process. In an expansion process, remember this, it is work done by the system, therefore it is positive work. In a compression work done on the system, it means pressure has to increase, therefore during a compression process, work done, it is negative. There is no work like negative work or a positive work based on the sign convention. For example, if I write minus 250 kilojoules, minus 250 joules, or else if I simply write 250 joules, the sign indicates this is the work done on the system. This is the amount of 250 joules of amount is required for the compression process. If I plus 250 joules, that is the work done by the system. This is the produced work. Therefore, sign indicates whether it is a work done by the system or on the system. Negative indicates it is on the system, and positive system, it is work done by the system. Next topic, it is work done in a frictionless quasi-static process or an equilibrium process. It's not equilibrium, it is a reversible process. Quasi-static. Another name for quasi-static process is reversible. Quasi-static. Infinite slowness in achieving the equilibrium state. That is quasi-static. Another name for quasi-static is reversible process. You can give this heading as the PDV work. PDV work is calculated only for a quasi-static work. Another name for that is displacement work. Let us calculate the work done. Expression for work for a reversible process. Let me consider a piston and cylinder arrangement. Let me name it as the figure A or something. Let us consider a piston and cylinder arrangement. This is the initial kind of state of the. Inside that cylinder, there is a gas which I am considering it as a system. The dashed line indicates we are considering gas as a system. This gas exerts certain pressure. Due to this pressure, piston will move upwards, and there is some external pressure which is behaving in opposite direction to the gas pressure, such that the piston is held in a equilibrium position, and that equilibrium position we are naming it as a state 1. Let me write this as a figure A. Next, figure B, I will write it, that is same piston and cylinder arrangement. Now the piston is at position 2. The piston is at position 2 or a state 2, that is equal, that is also an equilibrium condition. When it is achieved, is gas is the same gas, it is considered as a piston. After gas loses its pressure, that is when gas is exerting pressure, the external pressure is balancing and keeping this piston in a single equilibrium position. When we remove the external pressure, the piston moves upwards and reaches the equilibrium condition, that is equilibrium state, that is state 2. The displacement, the movement of the piston from state 1 to state 2, let us calculate as elemental distance, that is dl. Elemental work done, that is dw, which is calculated as F into dl. F into dl. Now we know that pressure, it is nothing but force by unit area. This can also be written as F is equal to P into A. Now I will substitute this F into PA to this. Therefore, dW becomes dW is equal to F can be written as P into A dl. Now this is area into length, that is volume, that can be written as dW is equal to P into dV, area meter square, this is meter square into meter, that will become meter cube. I can write dW is equal to PdV. This is the elemental work, but there is a change of state from 1 to 2. Therefore, change of state from 1 to 2, dW is equal to 1 to 2 PdV. And you are familiar with work is a path function. I can't write W2 minus W1, and also those are inexact differentials. Therefore, generally I will write W1 to 2 like this, and this is integral 1 to 2 PdV. This is the derivation of W1 to 2 integral PdV, that is for quasi-static process. Remember this, this integral 1 to 2 PdV work, it is for work expression only for the reversible process, or else you can call it that as a quasi-static process. Quasi-static process. W1 to 2 integral 1 to 2 PdV. This is the work expression. Very important, this one. You can remember this, W1 to 2 integral 1 to 2 PdV. This is W1 to 2 integral PdV. Very important expression. Now one more topic, that is point function and path function. What are this point function and path function? Let me write a PV diagram. Let us consider two states, that is state 1, and another state, that is 2. Now, a change of state taking place from 1 to 2, one to 2, by following a path. Let me tell that is path A. Similarly, it can follow path B to reach 2. One more process it can follow by following the path C. Therefore, there are three paths A, B, C in achieving the state 2. And if we recall, area below the curve in a PV diagram, it is work done. And the final states are same. Initial and final states in each process are same, but the path in which it is followed is different, and work done is also different. Therefore, work depends on path in which it is followed. Therefore, each W is different. Therefore, work is a path function. At the same time, one more energy, that is heat, that is work and heat, comes under path function. Then what are those point functions? These state variables, like if I draw here and calculate V1 and this one V2, and here it is P2 and this one as P1. Therefore, point functions are pressure, volume, and temperature. These are point functions. And for a reversible process, if I write 1 to 2 dW like this, and uh, mathematically, if you integrate this, you will get W1 to 2, and you will get what? W2 minus W1. Where is the W2 and W1? So where is the W1 depending on state? Where is the W2? Work depends on path in which it is followed. Therefore, I can't write like this work done, because work is the path function. Therefore, how will you write 1 to 2 dW? It can be written as W1 to 2 simply as it is, or else you can write like this W1 to 2. It tells the amount or quantity, that is area below the curve in a PV diagram. That is work done. Therefore, uh, integral 1 to 2 dW is not equal to W1 minus W2, or as W2 minus W2. It is not equal. Therefore, it is called as inexact differential. What? Inexact differential. Therefore, remember this, work is the inexact differentials, and also they are path functions. Similarly, we can write it for a heat, that is 1 to 2 dQ can't be written as Q2 minus Q1, because heat is a path function and also they are inexact differentials. Let me write it over pressure 1 to 2 dP. It can be written as P, limits are 1 to 2, and you can write P2 minus P1. Do you have P1 and P2 value in a PV diagram? Yes, P1 and P2 value are there in a, yes. Therefore, you can write similarly 1 to 2 dV, that is equal to V 1 to 2, and if you integrate it, you will get V2 minus V1. Similarly, for a temperature dT, it is equal to T, you will get limits are 1 to 2, P2 minus P1. Therefore, point functions are exact differentials. Remember this. Uh, Work and heat are path functions, and they are called as inexact differentials. And point functions are pressure, volume, and temperature. Pressure, volume, and temperature. Those are exact differentials. Next topic is free expansion with a zero work transfer. Let me consider one compartment, and which is isolated. Isolated means there is no transfer of heat and mass between the system and surroundings, not from inside to outside or from outside to inside. We had to use this hat symbol telling that there is no transfer of energy as well as mass. And this compartment is have a bifurcation, and that bifurcation, there is a partition in between those two compartments. The first compartment, there is a gas, and in the second compartment there is a vacuum. I will consider the same compartment which is divided by a partition. There is a gas and there is a vacuum. It is also isolated. Isolated. Now let me write this as a figure A and this one as a figure B. Now when I observe the figure A and figure B, what is the difference between this figure and figure B? I have written a dashed line. The dashed line indicates it is a system. Now gas plus vacuum comprises a system. Now when I remove the partition, what happens? Gas rushes to the vacuum side because vacuum doesn't offer any kind of a resistance. Vacuum doesn't offer any kind of a resistance. If there is no oppose, there is no displacement, then one will attempt to tell that work done is zero. Yes, that is true. Work done is zero. What about integral 1 to 2 PdV? You calculated the work expression. Is it a zero? No, it is not equal to zero. I will conclude it when I tell the figure C why it is. Now take the figure B where only gas is considered as a system. Here gas plus vacuum is considered as a system. Now gas is considered as a system. Now gas, when the partition is removed, if you neglect the work utilized in removing the partition, then vacuum doesn't offer any kind of a resistance also here. Therefore, one will say that there is no work done. That is W1 to 2 is 0, and here integral 1 to 2 PdV is not equal to 0. You can't tell this calculation of work in terms of integral PdV. When you will calculate integral PdV, work done as the integral PdV, when you will calculate W1 to 2 integral 1 to 2 PdV, if and only if the process is reversible. That is very important. Is there any process which is reversible? No. Therefore, you can tell work is as a 0, but what about integral 1 to 2 PdV? That is not equal to 0. Now, vacuum doesn't offer any kind of resistance. That thing we call it as a what? Free expansion. That's why the name work free expansion. In a free expansion process, work transfer is 0. When integral PdV is equal to 0, same compartment we will consider. It is bifurcated by a partition. And it is isolated. Now gas, which is considered as a system, and this vacuum is divided into number of strips, and every time when we remove the strip, it will achieve the equilibrium. Every time it also doesn't offer any resistance. Here also it doesn't offer any kind of resistance, but slowly, that's what we call infinite slowness. Which characteristics it is? It is the characteristics of a reversible process. Therefore, this figure C, whatever I written here, the vacuum is divided into number of strips, and at each succession stage, it will achieve a equilibrium state. Therefore, this process is a reversible process. Simply, you can tell vacuum doesn't offer any kind of resistance. Work done is 0, and at the same time, you can tell integral 1 to 2 PdV is equal to 0. This is also true for a figure C. Whereas in figure A and B, it is integral PdV is not equal to 0 because those two are not reversible process. You can tell vacuum based on vacuum, there is a free expansion, work transfer for a free expansion is on 0, and at the same time integral PdV is also equal to 0 because this figure C represents for quasi-static process or a reversible process.